Hi there, this is RuQing from the University of Tokyo. My talk in AHUG ISC21 is about tuning the portable dense linear algebra library BLIS for the chip A64FX, which implements a 512-bit SVE. Compared to more popular ARM-based processors, this implementation has a bit strong habit, which makes it a target requiring special care when we deploy our software. BLIS is a rapid instantiation framework for dense linear algebra subroutines with complete BLAS compatibility and many more operation supports. BLIS is based on the performance anatomy of GoToBLAS but was rebuilt in a modern way. Compared to GoToBLAS OpenBLAS, it reduced the number of kernels required from 3 to 2 and allows real number kernels to work directly for complex number operations with little performance loss. To start the introduction of this tuning work, let's first go a brief overview of the ARM SVE architecture. The scalable vector extension is a unified vector ISA targeting different vector lines for floating points as well as integer types. It allows all vector lines as a multiple of 128 bits through 2048 bits, with the 128-bit case very similar to the case of Neon in the sense of floating point processing behavior. And hardware implementation of SVE can choose a vector line suitable for their fabrications or application scenarios and adopt this software ecosystem. So currently we have 3 CPU implementations for SVE support open to the public. The first 2 are the next generation Neoverse chips by ARM, which is the HPC targeting Neoverse V1 featuring 256-bit vector line. The third one is A64FX by Fujitsu, come with 2 FPUs at 512-bit vector lines, and now already installed in the current world top supercomputer Fugaku. This is what we are gonna tune for our code today. A64FX is, well, as stated above, unique in many senses, among which a feature that directly impacts the way we implement our gem kernel is the difference between indexed and unindexed FMLA instructions. Well, FMLA instructions is, well, simply speaking, the batch, multiplication, and accumulation of vector elements. If only unindexed FMLA can be used for each vector of A and C, we have to broadcast elements of B one by one into the second operand vector. On the other hand, if we allow to use indexed FMLA, each vector used to store B can now contain more elements while defined by indexing range. For example, here, if we operate on double precision FP64, we can contain both the first element and the second element in B and dispatch 2 with one vector of B. On the other hand, if only unindexed FMLA is allowed, we have to occupy the whole vector for one B element. And for single precision, this problem is more severe because for single precisions, the indexed FMLA allows 4 elements in one vector. Well, of course, this does not directly affect the FPU throughput, but more registers spelled out means that more cycles for instruction wait, which finally affect the performance. As SVE defines 32 vector registers, assuming that L1 latency is comparable to the latency of FMLA instruction itself, we can deduce an optimal kernel size in the rightmost column, respectively. We see that indexed FMLA holds advantage over unindexed ones. This is also how most Neon kernels got implemented. However, for A64FX, the indexed FMLA approach is hurdled because the lack of multiplexer in this implementation. Indexed FMLA instructions use the FPU executing 2 micro operations for the single instruction. This fact is true even for floating point instructions executed in neo-compatibility mode, making previous ARM kernels basically unusable in this chip. Compared to the bottom rows with specifications given by Neoverse V1, we also see that A64FX has a quite large L1 FMLA latency. These altogether have made A64FX a very special target for tuning. Well, of course, as we are not only targeting A64FX, but also the generic SVE, our project contains both indexed and unindexed gem kernels, while only unindexed ones are merged for the moment. A more detailed introduction of these kernels will be given by the kernel author Mr. Stepan Nasir in this ISC 2021, and I'll skip these in my session. There's one other problem, it's about packing memory for gem operations. Packing columns into contiguous one can easily be done by loading and storing SVE vectors. On the other hand, when we want to pack column major matrix into row continuous storage, the choice diverges here. The first way is to use the gather log. Directly load these column stored matrices in rows and store them contiguously. Where there is another way of use the in-register transposition. We load several columns of B at once and do a transpose within these loaded vector registers. As SV assembly is somehow agnostic to VL, this approach is in many senses unnatural. It requires vector length specific coding and preparing a bit complicated predicator configurations. However, for this moment on A64FX, the in-register transposition is a little bit superior to the straightforward way.
Now, let's take a look at the full performance graph. The first thing I want to show is about this triangle solver, as BLIS needs both gem kernel and triangle solver kernel to unleash the full power of all operations. We only implemented gem kernel this time, so the triangle solver is not comparably good to the vendor BLAS called Fujitsu SSL2. However, if we look at gem, we see that our performance is decently good, and in larger matrix sizes, we can even achieve a higher performance than the vendor's BLAS. A complex case is another small weakness. I've not written native complex number kernels, but relied on BLIS framework to push real kernels to complex numbers. This somehow increases memory access. It has somehow lowered the performance. Now, let's look at those symmetric and triangular matrix operations where BLIS shows its true power. With BLIS, only one gem kernel extracts maximal performance for all these operations where the vendor fails those per operation tuning. Here is another performance graph with full node execution. Full nodes means all 48 cores, each core one thread. This graph we can see that BLIS can overtake vendor's lead in almost all cases, even for those triangular solvers. This manifests BLIS' way of threading. To wrap up, we've tuned BLIS for A64FX processor, especially for its own implementation of SVE. The last bit performance improvement is done with in-registration transposing and some other code optimizations. Performance is generally above the vendor BLAS in many extents thanks to the framework advantage of BLIS. Finally, please allow me to introduce a bit potential applications of this work. First, BLIS is very extensible to implement new operations. We can extend this framework into like antisymmetric matrices for German wave function in quantum chemistry and condensed matter physics. I personally has optimized an application called NVMC for processing with German wave function in condensed matter physics and achieve a decent speedup. The second one is direct support for generic stratus storage, which means that the matrix is neither stored column major nor stored row major. In most cases, we copy those matrices into an out-of-space memory block and use BLAS operations there. But this is creating extra memory cost as well as extra memory access time. To solve this problem, BLIS is supporting as well generic stratus storage. This can greatly speed up some automatic differentiation implementations, like the forward differentiation in Julia. Further, we can directly probe BLIS way to tensor operations. We already have an implementation called TBLIS, and I have also ported my kernels into TBLIS, but it's not merged yet. We have Julia wrappers for TBLIS like tbliss.jl and blade contractor.jl by myself.
I honestly hope that one of these packages might be really helpful in those HPC related researches. This is the end of my talk today. Thank all of you for your attention and time. Thanks.